Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 6B of this capacitors topic, and this will be the end of electrostatics chapter. So electrostatics has been ended, and if you have come until this point, right, trust me, you have already covered like 70% of the syllabus, because mainly in electromagnetic fields, electrostatic is the most important and most difficult topic. Okay, after that in magnetostatics we'll study few simple things that will be related to electrostatics, so we can relate. So if you are planning to start magnetostatics from scratch, and if you haven't studied the first chapter, I will highly recommend go through the first chapter, will complete the PYQs and then come to the magnetostatics chapter, because that will be related to this electrostatics, and there I will go a bit fast because I am hoping that I have already taught you the basics. So there I will pick up from that and I will go to the advanced levels topics. Okay, so before starting, obviously in today's lecture we'll study about dielectrics. That will be a short topic, and obviously I will solve the homework assignment questions that I gave you in the previous lecture. So first of all, we'll obviously solve all those questions, and though like many of them were very interesting questions, so we'll solve all those questions. So at first, this one was the first question as homework. I will just check whether I gave any previous question as homework or not. No, I didn't give. Okay, this one was only the first question as homework. Okay, so we'll start with this. So here, what do we have? This is a gate 2014 question, and we have been given the C0 is the capacitance of a parallel belt capacitor with air as dielectric, as shown in figure A. Okay, if the air is in dielectric for the whole capacitor, only air is the dielectric, then what is the capacitance formula? C0 they have given me as epsilon naught A by D. Correct. This is the parallel plate capacitance formula. This is equal to C0. That is what given. That is what is given in the question. Okay. Now, if half of the entire gap as shown in figure B is filled with a dielectric of permittivity epsilon r, the expression for the modified capacitance will be with respect to the previous capacitor. So here half of the capacitor is filled with dielectric. Now, is this a series connection or a parallel connection? So if I observe here that the tangential components are same, right? Here electric field will flow from this top to bottom or bottom to top. So I can observe on the interface, it is tangential to the medium to the interfacing region, right? So obviously, as it is tangential, what can I comment? Electric field is tangential, hence obviously capacitors are in parallel. So that means if this portion has a capacitance of C1 and this portion has a capacitance of C2, then C equivalent will become C1 plus C2. So C equivalent will become C1 plus C2. So what is C1 basically? Now here I observe that previously the width of this was totally B. Now this has been half, right? So currently, previously I just show you pictorially, this was B. Now this has been halved. So this has now become B by 2 and B by 2, correct? So the area has been halved basically, because this like the length is remaining same. So obviously the new A dash of both of them is A by 2, and because it is simply L times B, A times B, and A is remaining constant because this length, right? This length is constant, just this length is changed. Okay, and the distance between the plates is same, so that will remain same. Everything else is same. So my C1 will be what? C1 is again in vacuum, so it will be, you can go in the next page actually. C1 is epsilon naught A by 2 divided by D. C2 is epsilon naught, and epsilon r is also there, right? Because there is an extra, like it has a permittivity of epsilon r. So I will write that expression, epsilon r A by 2 divided by D. So this one will become like this whole thing is, except the epsilon r, this whole thing is what? C naught by 2. And this is what? This is C naught by 2 itself. And obviously there is an extra epsilon r here because this is multiplied. So obviously what will be the total capacitance? Total capacitance will be C1 plus C2. So I will take C naught by 2 common. This will be 1 plus epsilon r. So your option A will be correct in this case, right? So one thing I wanted to say is that like you could have done with electric field, because the tangential components must be same. Another thing what you could have done is the simple thing, right? What is the simple thing? You could have told that the potential difference between these two plates and these two plates are same, so they are connected in parallel. Okay, like that also you can do. Okay, whichever is suitable, or these two plates are sharing the charge. Okay, so I hope you get the point. That's basically it for this particular question. Now we'll move on to the next question. So the next question, we have like a spherical capacitor like configuration, and you had to find out the basically what determine the in the figure, if the figures represent the cross section of two spherical conductors, determine their capacitances 1 and 2 and A, B, R, C and given. So here I can observe that I am like in case 1, right? Medium is varying with respect to R, right? R vector, with respect to R vector. So I'm varying radially outward. I'm varying radially. Okay. So for this, the simple formula is what? Simple series formula, because here electric field will be radially outward and medium is also varying radially. So in all the mediums, electric flux density will be same. That is normal component will be same as it is normal. So obviously everything is in series. Everything is in series. So what can I comment? I can comment that series combination. Okay, series combination means my C equivalent will be, there are two capacitances, one due to this medium, another one due to this medium, correct? This is epsilon R2, this is epsilon R1. Remember, they have been flipped now, so just be careful about that. Okay, so it will be C1 C2 divided by C1 plus C2. So what else can I say here? So I can say that my C2 where did it go? Yeah, my C2 C1 will be what? Basically, if you remember the formula, it was what? 4 pi epsilon in its own region. What is the epsilon? Epsilon is in this region, right? It is epsilon R2. So it will be epsilon naught into epsilon R2 divided by 1 by the lower radius divided by the higher radius. So it is A by C. 1 by A minus 1 by C. Okay. So I hope you remember how to recall this formula. Okay. So what is epsilon R2? Epsilon R2 is 3.5 simply. Okay, epsilon R2 is 3.5 simply. So we will place that value. So 3.5 4 pi epsilon naught 3.5 1 by A. Now this is in centimeters, so, or this is in millimeters. So I will keep it in millimeters for now. Later on I can change, or we can do it in meters as well. I am doing it in meters. 1 by 1 minus 1 by 2 into 10 cube, because it was in the bottom 10 raised to the minus 3. So this is the this equation. And what is C2? C2 is, just hold on, 4 pi epsilon naught epsilon R1 actually, because epsilon R1 is between the medium interface, right? Epsilon R1 1 by this time it will be 1 by C minus 1 by B minus 1 by B, which is equals to 4 pi epsilon naught. Epsilon R1 is 2.5 divided by 1 by B is 1 by C is 1 by 2, and this is 1 by 3. 1 by 2 minus 1 by 3 into 10 cube. So I will just simplify this further. So 4 pi epsilon by 10 raised to power 3, right? I can write this as a constant, any constant, right? So I can write this as a constant C. Okay. So I'll assume that my 4 pi epsilon naught, just for simplification of calculation, by 10 raised to power 3 is a constant C. So this will become what? This will be 3.5 divided by 0.5 C. This will be 7 C, and this will be 2.5 divided by 0.5 minus, okay, so this will be 3 minus 2 by 6, 1 by 6. This will be times 6 C. So this will become 12 and 0.5, 15 C. Okay, this will be 15 C. So now I can simply find out the C equivalent. C equivalent means what? 7 C into 15 C divided by 21 C. 21 or 22? Sorry, not 21. 22 C. Okay, so CC will get cancelled. So this will be 7 into 15. So that is 7, 15, 105 C. What am I doing actually? Yeah, 105 C, and this is 22. Correct. Now can this be can division of this further is possible? No, division of this further is not possible. Now what is the value of C actually? If I just compute this value real quick, just compute this. This will become I can write this here itself. This will be equals to 105 divided by 22 into 4 pi 8.854 into C. Okay. So this will be 8.854 into 4 into pi divided by 22, and this raised to the power 10 raised to the power minus 12. This is getting divided by 10 cube. So just really checking real quick what is okay, divided by 22 is done. 10 raised to the power minus 3, correct? Yeah, this is totally correct. 10 raised to the power minus 12 pi into, okay, 105 actually missed. 105 by, okay, 22 I divided by twice. Actually, this is wrong. Just hold on. 105 divided by 22 into 4 into pi into 8.854 divided by 1000. Yes, 0.53. Okay, so 0.53 picofarad. This will be 0.531 picofarad. This will be the C equivalent for the particular system. This is a good question. If we are varying the medium along the radius, along R. Okay, what about the second one? What is happening in the second one? So in the second one, if I am observing that my medium is varying along what they have given me, right? Phi is varying from 0 to pi. Okay, phi is varying from 0 to pi. So they have given me that medium is varying along phi. Medium is varying along phi. Okay, how does phi vary actually? Phi varies from 0 to 2 pi, but here medium is varying from 0 to pi. And what was the formula that I told you to remember? So whenever you are in the exam hall, in the rough notebook, just write this down, so that this is how you are able to recall the formula. So you will write this 0 to 2 pi d phi, right? This was the formula for the phi coordinate. And what was the actual formula? So here what I written was 2 pi times 2 epsilon naught divided by 1 by R1 minus 1 by R2. So this 2 pi was coming from this, right? If you recall, like I just wrote the formula here for phi. For phi it was simpler. This 2 epsilon naught was on the outside, and this 2 pi was coming from this, right? So yeah, exactly that is what I have done here. Actually, that is what I have done. So like this, you can recall the formula. Even if you tend to forget the formula, right? This is the way you can recall the formula. So I'll just replace it for the when my phi is varying from 0 to pi, I have epsilon R1. So this will be 0 to pi d phi into 2 into epsilon naught into epsilon R1. Again, epsilon R1 is same only, right? Epsilon R1 is same only. It is 2.5. 2.5. So we'll write this epsilon R1 for now, divided by this radius will be same, right? this radius will be same. This is A and this is B. Now the radius doesn't change anymore. So it is 1 by 1 minus 1 by 3. Okay. 1 by 1 minus 1 by 3. Okay. So this will I will just again take a simple like common term. So what I will take is this 2 and this becomes pi, right? 2 epsilon naught pi divided by this is 1 minus 1 by 3. This I can take common as C. Correct. Epsilon r1 can remain otherwise. So this will be C, and epsilon r1 is obviously there. Epsilon r1 is obviously there, and this time like if it is varying along phi, right? What is happening? That means it is tangential. That means I will have parallel, right? Parallel combination. So my C equivalent will be C1 plus C2. So this is my C1 basically. What about my C2? C2 will be same from phi to 2 from pi to 2 pi d phi into 2 epsilon naught. This time it will be epsilon r2, and this radius in the bottom will be same 1 minus 1 by 3. So this is simply epsilon r2 into C. So this becomes what? My C equivalent becomes what? My C equivalent is C into epsilon r1 plus epsilon r2. So what is C basically? C is this thing. So it is this will become 2 by 3. So 2 gets cancelled, 3. So 3 epsilon naught pi into epsilon r1 plus epsilon r2, which is 2.5 plus 3.5, which is 6. Correct? 2.5 plus 3.5, which is 6 simply. So this will be 18 into 8.854 into 10 raised to power minus 12 into pi. So we'll just quickly solve this thing. So if I quickly solve this thing, right? 18 into 8.854 into pi. Okay. And if I do okay, I forgot one thing, that this was in millimeters, right? So there must be a 10 cube here. This was in millimeters. Okay, just converting everything into meters. Correct. So this one will be divided by 10 cube. So this will come out to be 0.5 picofarad. Okay, C equivalent will be 0.5 picofarad, almost same as the previous case only, but it's a bit different. So you can observe that if we are varying parallelly, answer will change. And how do you find out if they are varying parallelly or not? I have told you with basics, right? With electric field, no one will show with electric field. Okay, so there is one simple question they have given. This is also a good question. Two spherical conductors A and B of radii A and B, where B is greater than A, are placed concentrically in air. So this is a spherical capacitor configuration. The two are connected by a copper wire as shown in the figure. The equivalent capacitance of the system. What will be the equivalent capacitance of the system? So if the two are connected in between, right, with a copper wire, what happens? What have we studied in the previous lecture or the lecture before that? If the two any conductors are connected with a copper wire, the potential becomes same. If the potential is same, there is no potential difference between these two. There is no potential difference between these two. These two act like a single capacitor. What will happen is that if I give a plus Q charge here, okay, if I give a plus Q charge, I will just show you. If I give a plus Q charge in the bottom, okay, if I give a plus Q charge, like what is happening? What was the general method for finding capacitance? Give plus Q charges and see what is the potential difference, right? If I give a plus Q charge here, I will just show you with my own diagram itself. I will draw two concentric hollow conductors. Okay, what do I know? What will happen? If I give a plus Q charge here, what will happen? I know inside a conductor electric field cannot exist. So what will happen? This outside conductor, right, will generate minus Q charge here, and on the outside it will generate again a plus Q charge here. So that it was initially electrically neutral, it will be again electrically neutral, but somehow I provided plus Q charge here. I made that change, and due to that change automatically this happened. Okay, so like I hope you have studied the cavity part. There I have explained this very good. I will not explain that here, like I will not take up much time here. So it will generate plus q charge again outside. Okay, so the inside thing doesn't form a capacitor. Actually, there is no potential difference, right? There is no potential difference. This doesn't form a capacitance. But the outside, can I say the outside? What is the outside? Outside is like a sphere, isolated sphere charged with q. Correct? If it is isolated sphere charged with q, what will happen then? Then simply this will be the formula of the capacitance for a isolated pair, or like just for isolated sphere. What was the formula? It was 4 pi epsilon r, and for what is the radius for outside? It is b, right? It is b, so it will be 4 pi epsilon b. So option C will be correct. Like these type of tricky questions also should come, so that's why I'm training you this type of questions as well, so they can ask you these simple questions. Like this doesn't need much calculation, but what you need is to use your brains and and be a bit smart. Okay, that's the main thing that you need to do. So another similar type of question is this. Can you pause the video and try it for yourself? Two spherical conductors A1 and A2 of radii R1 and R2 are placed concentrically in air. If A is given charge Q while A2 is earthed, then the equivalent capacitance will be. What will be the equivalent capacitance? You might say, sir, this is earthed, this has zero charge, this has this zero potential, this has V potential. So you will say that your capacitance will be what? Your capacitance will be just due to this sphere, because this is isolated and this is earthed. I will say wrong. Okay, again you apply the same general principle of two concentric spheres. If I have two concentric spheres and they are not connected the same, so there is some potential difference between them. So what will happen is that, although this is not a great drawing for sphere, so I can say that if I provide a plus q charge here, and you will say this is grounded, automatically a minus q charge will get generated here, and this doesn't need to be neutral. Why? Because all the charge will be provided by the ground. Okay, ground has infinite amount of charge. It can sink in infinite amount of charge and it can give infinite amount of charge. Okay, all the charge will be provided by the ground. So here I will generate a minus q charge, and nothing will happen. If you ground this, nothing will happen. Even if you ground this also, nothing will change. The formula for capacitance which we derived in the previous lecture in the first lecture will still be same. What was the formula for capacitance between two concentric spheres? It was 4 pi epsilon divided by 1 by R1 minus 1 by R2. Here what was the R1 and R2? It is they have given epsilon naught, and R1 is inside, R2 is outside. Fine, epsilon naught. So I can further rewrite this. I don't prefer the other way of writing the formula, because this is more easier and to understand and remember. But in questions they can give this method of writing the formula as well. It will be, if I just multiply R1 R2 on both sides, on top and bottom, so it will be 4 pi epsilon naught R1 R2. This one will become R2, this one will become R1, R2 minus R1, and exactly that is what is present in the option A. So your option A will be correct in this case. So these are a few tricky questions. These questions can get asked. Okay, can be asked on the exam, and I'm expecting these type of questions will be asked in the future. Okay, so now this is again a similar concept, right? Just here what is happening, this is a top view of a cylinder. This is not a sphere anymore. So what is the top view of a cylinder? What can I observe? I can observe a disc. Just if I have a cylinder like this, right? This is okay. This is not like a cylinder. I don't have any. Okay, the bottle I have, right? So if you see the bottle, what is the top view of it? What is the top view? It's just like a disc, right? Just like a disc. So it will be just like a disc. Okay. So the top view of it is just like a disc. So you are observing coaxial cylinders. These are coaxial cylinders whose axes are same. Okay, here I am varying with respect to radially. Again, it is normal, right? It is normal. The electric field is normal with respect to the interfacing medium. So obviously what will happen? Obviously I will be again solving with using the series formula. This will be the simpler one. Here again, what I am observing here, my phi is varying. They have given me, generally they will give you what is varying. So if phi is varying, right? If phi is varying, so I am varying with respect to the x. So if phi is varying, that means again they are in tangential, because here electric field will be something like this, and here also electric field will be something like this. So it is tangential, right? And in tangential they are parallel formula. And what is the formula for phi? That we already know. So if you remember the formula for the capacitance for the first case, First case is medium varying radially. Okay, if medium is varying radially, so medium varying radially meaning along R. If it is varying along R, so my C equivalent will be C1 C2 divided by C1 plus C2 as they are in series. And what is C1 basically? It will be 2 pi epsilon 1 into H divided by the ln of bigger radius and lower radius. That's how this ln will come out to be positive. So it will be bigger minus lower. So bigger is in this case C by A. Okay, so just remember this, that this epsilon height they have given 10. Okay, H they have given us 10. That all those things I will put later on, and C by A I will write, and this will be simply epsilon R2. Please remember, between A and C I have epsilon R2 and not epsilon R1, so don't make that mistake. So 2 pi epsilon R2 epsilon naught H divided by ln C is what, as they are in ratio, right? C by A is in ratio, so I can choose both in millimeters, no worries. Millimeter units would get cancelled. C by A is 2 by 1. Okay, so I can again write C is equals to 2 pi epsilon naught H. So this will come out to be epsilon R2 is how much? Epsilon R2 is, okay, I've forgotten to write it. Epsilon R2 is actually 3.5. Epsilon R1 is 2.5. Epsilon R2 is 3.5. Okay, so 3.5 by ln to C. What about C2? C2 will be 2 pi epsilon to H ln B by A, which is 2 pi epsilon 2 is epsilon R1, which is 2.5 H ln B is 3, I believe. Yeah, 3 by 1. So it will come out to be 2.5 by ln 3C. Now I'll just use the simple parallel formula. So what is the parallel formula? C equivalent will be 3.5 by ln 2 into C into 2.5 by ln 3 into C divided by, I can take the C common, 3.5 by ln 2 plus 2.5 by ln 2. So this will come out to be what? C equivalent. So CC will get cancelled and ln 2 ln 3 can get multiplied. So 3.5 into 2.5 into C divided by this will come out to be ln 3 3.5 ln 3, both ln 2 ln 3 will get multiplied, plus 2.5 ln 2. Very weird expression, but still expression nonetheless. Yeah, this is what we will get. So I will just simplify these things a bit. So ln 2 into 2.5. Wait, am I correct here? 2.5 by ln 2. Yeah, 2.5 by ln 3. Okay, sorry, I made a mistake. 2.5 by ln 3. This should be ln 3. Sorry, this should be ln 3. Yeah, this is ln 3. Fine. This is ln 2. Yeah, this is ln 3. This is ln 2. Yeah. So ln 2 into 2.5 plus ln 3 into 3.5 into 3.5 into 2.5. So this is 1.57 into C. What is C? C is 2 pi 84 into 1 10 to the minus 12 into 2 pi epsilon into height, right? Height was 10, which I remember. Height was 10. Yeah. So if I simplify this into 2 into pi into 8.854 into 10, yeah, this will come out to be a lot actually. So this will almost come out to be 0.873 nanofarad. Okay, this will be my C equivalent for the case 1 when they are varying radially. When they are in parallel, for the case 2, medium varying along phi. So basically electric field is tangential, so parallel. So if they are parallel, my C equivalent will be C1 plus C2, correct? So what does my C equivalent become now? So it is pretty simple. I'll just write down the formula. Okay, write down this formula. How do you remember the formula? You write down the main formula. Okay, and from here you can identify that this 2 pi is the main thing, right? 2 pi is the main thing. Okay, 2 pi is the main thing. So I can write down that this is equals to 0 to phi d phi epsilon h by ln c by a, not c this time, it is b by a only, because there is only 2 concentric cylinders. Okay, yeah, b by a. B is 3, a is 1. So the first one will be pi epsilon r1 epsilon naught, because this is epsilon r1 I believe. Yeah, this is epsilon r1, yes. H divided by ln b by a. Again I can write something as c. C will be what? C will be pi epsilon naught h by ln b by a. So this is simply epsilon r1 is 2.5, right? Epsilon r1 is 2.5 I believe, yes, 2.5 c, and epsilon r2 will be, it will be 3.5 c. So your c will be 2.5 plus 3.5, that is 6c, which is 6 times pi epsilon naught, that is 8.854 into 10 raised to power minus 12 into height is 10 and divided by ln 3 this time, because it is ln 3 by 1, right? So what will it come out to be? 8.854 into 6 into pi in, okay, something I made a mistake, 8.854 into 6 into pi into 10 divided by ln 3. This comes out to 1500. If I divide this by 10 cube, this is 1.51. okay, so yeah, this comes out to be 1.51 nanofarad. Okay, so am I making any mistake? No, this is b on a only. Yeah, b is here. Yeah, 1.51 nanofarad. I just wanted to check quickly a thing, and 3ln divided by 2ln, yeah, 2, yeah, this is correct. This answer is correct, 1.51 nanofarad. This will be your C equivalent. Okay, this is not C, this will be your C equivalent, and this will be your answer. Okay, so these questions can come, simple question. This question, one of these questions has come on gate, so that's why it's very, very important to study, because this came recently only 2019. So that's why I was putting so much stress in this. So here I have two coaxial cylinders. Coaxial means they are having same axis. Okay, shown in figure 1 with relative permittivity epsilon r2, epsilon r1. When 1/4 of the dielectric portion is replaced with another dielectric related to the permittivity epsilon r2, the capacitance is doubled the value of epsilon r2. So this thing is very, very interesting, right? Question is very, very interesting. So here I'm observing it is varying with respect to what? Z. This is the top view, right? This is just a top view if you observe. So this is a top view, so it is not varying along the Z, it is varying along the phi. Again, the first point that I will write is medium varying along phi. So if medium is varying along phi, what can I say? Then they are simply connected in parallel. Okay, so my C equivalent, and why they are in parallel? Because electric field is tangential. All these things you know, C1 plus C2, right? So basically for the first case, right? For the first case, what is C initial? C naught. Capacitance for the first case. C naught is simply this formula. What is the formula? Formula is 2 pi epsilon epsilon into H divided by ln capital R by small r, right? Capital R by small r, higher by lower, correct? Else it will be negative. What is this equals to? This is 2 pi epsilon naught, and what is epsilon r? Epsilon r is 2. Epsilon r is 2 into H divided by ln capital R by small r. Okay. So now we know this. This is my C naught. I will keep this. I will keep this for now. And what is my C1? C1 will be simply C1 simply, if I like say C1 is what? This 2 pi thing, right? This 2 pi thing will get replaced with this. So C1 I can write it is lying within epsilon R2, and C2 is lying within the other quarter, right? So 1/4 of the portion has been written. So epsilon R2, the medium is epsilon R2 for phi equals to, let's say I am varying for phi equals to, I can take any reference. So I am taking this as reference right now. Okay, for phi equals to, it doesn't matter, 0 to phi equals to pi by 4. I can take any reference, it doesn't matter. Okay, so this will be what? Simply here, if you remember phi comes, so it will be pi by 4 into epsilon naught epsilon R2 into H divided by this bottom thing will be same, right? Ln capital R by smaller. Now what is this actually? What is this actually? So this thing, right? Epsilon, no, pi pi was there previously, no, 2 pi was there. Okay, so actually what I can do, I can take the constant terms outside. Okay, so this pi epsilon naught H ln capital R by R, this is, let's name this as C dash. Okay, so this will be 4 C dash, where C dash is pi, all the constant term, this will never change. Okay, epsilon naught H divided by ln capital R by R. Okay, so this will be pi is there, 1 by 4 will be outside, epsilon R2 they haven't told me about, and yeah, this is the only varying term, right? So this will be C dash. What about C2? C2 will be the remaining 3 by 4 pi, right? 3 by 4 pi, no, it will be the remaining total 2 pi, right? I have 2 pi, so pi by 4 if I subtract, it will be 7 pi by 4. Okay, the remaining portion will be 7 pi by 4. Okay, I'm a bit wrong actually. This is pi by 2. If the quarter 1/4 portion is given, this is 1/4 is 2 pi by 4 is pi by 2. Sorry, I was just thinking about quarter circle, so it will be pi by 2. Why this is pi by 2? 1/4, that is overall angle is 2 pi divided by the 4 is pi by 2 simply. That's why. Just a mistake on my behalf. So this will be 2. This will be 2 epsilon R2 C dash. Okay. What other portion is remaining? Other portion 3 pi by 2 is remaining, right? So this will be 3 pi by 2 epsilon naught epsilon R1. Epsilon R1 is how much? I will write that later on. Into H divided by ln capital R by smaller. So this will come out to be 3 by 2 will be outside times epsilon R1 is 2 into C dash. So this will be C dash, 3 C dash. Okay, so but my overall capacitance is what? It will be parallel, right? C equivalent, it what is what? This is epsilon R2 by 2 C dash plus 3 C dash. Now this is equals to what? They have told me the capacitance is double. The final capacitance here is double if I place this dielectric. So what was the initial capacitance? It was 4 C dash. So the final capacitance will be what? 8 C dash. This will be equal to 8 C dash. So C dash gets cancelled. So I am left with this equation, epsilon R2 by 2 plus 3 equals to 8. So my epsilon R2, this is 5, 10, simple 10. So your epsilon R2 comes out to be 10. and this will be your simple answer. Okay, so these type of questions actually has come up recently, and this is a very very good question because they just haven't simply asked you to find out the capacitors. They just have asked you to find some relative parameter. So computation is simple, but thinking procedure is a bit different. Okay, that is a bit difficult. So obviously now we'll start with today's lecture, that is the topic about dielectrics. So what are dielectrics basically? So we will study all those things which we already know. We'll solve the questions. Even if you didn't study about dielectrics, right, you could have solved all the questions that I will solve in this lecture. But few new terms you should know about dielectrics. If some theoretical questions may get asked in examination, those you will be able to answer. So first of all, dielectric is what? Non-insulator, which we already know. So a non-conductor or insulator, non-conductor, it is an insulator which is a non-conductor. Okay, and it is a non-conductor or insulator that does not allow free movement of charges, as it doesn't have many free charges left, meaning it has few or no free charges. Uses often used as a protective coating around electrodes and connecting wires. So dielectrics are often used as a protective coating around electrical wires because the wires, okay, they will pass electric current, but we cannot touch the wires, right? We will get shock. So we have to have electrical coating so that no electrical current passes through the dielectric, and those are actually used in capacitors as well, in between the plates, metal plates. So examples: dielectrics, common insulators. In like, what are the examples of dielectrics? Such as porcelain, ceramic, mica, glass, plastics. These are common example of dielectrics. Okay, this is the protective coating for a like around a metal plate. Okay, so these are a few things that you should know. And now dielectrics have two molecule types. What are the two molecule types? One is polar molecular, one is polar molecules, and another one is non-polar molecules. Okay, so first we'll study about polar molecules. What are polar molecules? Polar molecules have permanent dipole moment because the centers of positive and negative charges do not coincide. What I mean? Just like this is just a chemistry example. Don't worry if you didn't understand this theory. Not that important. You can take this theory totally lightly, but it's my duty to teach you everything. So let's take this example of H2O. So in H2O, what happens? So if you know, remember that in H2O, the H molecules are present somewhere here and O molecules is present somewhere here. This is for chemistry. Don't worry if you couldn't understand this. You can take this lightly totally. This is not that important. Okay. So here, if you remember, it was H plus O minus, right? H plus O minus. But what is the direction of dipole? It is from negative to positive. So direction of dipole moment will be something like this. This will be the direction of dipole moment for this particular combination P1, and this will be the direction of dipole moment for this particular combination P2. Okay, so direction is from negative to positive. Their centers are not aligning with each other. We'll see this for the second next type of molecules, that is non-polar. Here also HCl, it was H plus Cl minus. So again, like in chemistry they told it the direction is like this, but in physics the direction is just opposite. Everything happens opposite, right, in other subjects. So it is from negative to positive. So this is the direction of dipole moment, and they have some non-zero dipole moment. But what about this type of molecules where the centers are aligning with each other? That is also a possible type of molecule. Non-polar molecules do not have a permanent dipole moment. Their positive and negative charge centers coincide. If they are coinciding with each other, right, they don't have a dipole moment because their distance is zero. They don't have a distance itself, right? They don't have a dipole moment if they are colliding with each other. Induced dipole moment. In presence of an external electric field, the non-polar molecules can develop an induced dipole moment. How? What will happen? Let's say there are two charges. One is positive, another one is negative. Okay. So if some electric field comes, external electric field comes. Okay. External electric field is coming. Now, if external electric field is coming, then this positive charge will feel a force on the right hand side, correct, and this negative charge will feel a force towards the electric field, that is on the left hand side, correct. So what will happen? The dipoles, like this particular combination, will get distorted. Plus will go on the right, negative will go on the left. Hence what will happen? The P net, right, net dipole moment will become non-zero. Why? Because there will be some distance between them, and that distance will cause some dipole moment. Okay, but before, as this distance was zero, there was no dipole moment, right? P net initially was zero, but final it gone to non-zero. Okay, that is what happens, and there are a few real life examples. Just take the example of CO2. Just study about CO2. I will not go in depth of that because that is not required for an examination. But for carbon dioxide, right, the molecules are actually placed on over each other, okay, on the centers. hence there is no dipole moment initially. But obviously if I place it in influence of an external electric field, there will be a dipole moment, there will be a induced dipole moment. That type of dipole moment is called induced dipole moment. So anyhow, if there is some electric field, there will be some dipole moment. Hydrogen also has H2 are also non-polar molecules. Okay, so here net what I need to go through, like in summary, what I wanted to understand is that in dielectrics the net dipole moment per unit volume is zero in absence of an external electric field. Why is that the case? Because what will happen is that in dielectric there will be, like, there are very less free charges. They are just present in pairs, like positive and negative are present in pairs, right, in dipoles, and they will be some distorted like this. But the net dipole moment of all of them, right, due to this dipole moment is in the dipole moment due to the non-polar molecules is anyway zero. Correct. Non-polar molecules, the dipole moment is zero. Due to the polar molecules, the dipole moment is non-zero. But if I place it in a dielectric, right, if all thousands, millions of dipoles are present inside a dielectric, because there are no free electrons. So what will happen? This will cause a dipole moment in this direction. This will cause a dipole moment in this direction. This will cause a dipole moment in this direction, in this direction, in this direction. So all of them net will actually cancel the dipole moment. So P net, if I add each dipole moment, right, and sum those vectorically, sum these things, they will be net zero. Okay, P net will be zero. It doesn't matter. But why are they in a non-uniform manner? Like, why are they not in a straight manner or like perfectly aligned? Why are they not aligned? They are not aligned due to these dipoles are not aligned due to thermal agitation. Okay, they are not aligned due to thermal agitation. Why? Because at room temperature 23 degrees centigrade, the molecules gain some kinetic energy, and due to the kinetic energy they move. Okay, just slightly they move, and due to that they have some movement, and that is known as thermal agitation. Don't need to go much 2 minutes into that. Just understand that they will not be aligned when they are just placed without any external electric field. Now what will happen once I place external electric field? All the dipoles will get aligned. Okay, as they have some dipole moment, this the polar molecules already had some dipole moment, but the non-polar molecules, a dipole moment will get induced. How will it get induced? So I will explain you. Just actually what happens inside a capacitor, that also I will explain. So here let's assume these are the two plates of a capacitor, right? Metal plates of a capacitor. Now electric field, external electric field I am applying. Okay, if I am applying external electric field, what will happen is that due to the dipole moment, right, the dipoles will get aligned on the direction of the electric field, and due to this electric field, all the negative charges will get attracted here, and all the positive charges will get attracted here, right, on the right hand side. They will get repelled here, and all the negative charges will get attracted here. But not all the free negative charges and the free positive charges, because basically in dielectric there are very few, limited amount of positive and negative charges, right? Free, I'm talking about free charges. But all the other dipoles will just get aligned. These dipoles will get aligned. That's it. Okay. Now what will happen? Due to this positive and negative, an internal field will get induced. This is known as the induced electric field. Are you able to recall that this is the same story as the conductors? What was the story for conductors? The story for conductors was simply that an internal electric field will get induced, right, in conductors, and that will cancel out the external electric field. Hence the net electric field inside the conductor was zero. Okay, but here it will not be zero. My E induced will be less than E. Okay, why is that the case? Why is E induced less than E? Because I have less free charges. There I had abundant amount of free charges. It can generate any amount of electric field it wants. But here I have some limitation. I can only generate so much of electrons, right? Less free charges. But obviously what will happen? Overall electric field in this region, right? Electric field in the dielectric will not be equals to E in E. Electric field in the dielectric will actually be E minus E induced. Now you might say, sir, what are you saying? What are we saying? Are you teaching something new? No, we have already used this concept. in the whole capacitor. We actually have already used this concept, but I haven't explained because it was not required there. Okay, I didn't want it to get confused. Okay, it was not required. Now what will happen? Why did they get aligned? Because if you remember, there was a torque getting produced, right? P times the electric field, P cross E, a torque was getting produced, due to which all the angle between the E and P dipole moment gets 0. Okay, if you remember, we study about dipole moment and rotation of dipole moment, all those things we studied, right? And due to that, all of the inside dipoles will get aligned. Now, what will happen is that, let's say my initial electric field, external electric field is E naught, my induced electric field is E induced, E net will be the net electric field, which will be equals to what? So external electric field is E naught and induced electric field is E induced. So total electric field, what will be inside here? It will be simply E naught initial electric field minus the E induced. Okay, this will be the total electric field. Now this actually, E net has a special name. What is the special name for this E net? E net is equals to E naught by K basically. Okay, and what is K? K is the simple dielectric constant that we have already used. So don't worry, this is the same thing that we know. Okay, so just in a different way they teach you. So it is a dielectric constant. And is there any limit to this E net, right? Yes, there is a limit to this E net. It is a dielectric breakdown. So if I keep on increasing my E naught, I will keep on increasing my E naught. What will happen? My E net also will keep on increasing. After a certain stage, what will happen is that this dipoles, right? This dipoles has so much strength. Okay, you are keeping these two pens. This two pen is a single object. But if I try to break it, just give it a little bit force, it will not break. But if I give huge force, right, it will break. And exactly that, the same thing will happen. I told you dipole acts as a single molecule only. Wherever this positive charge will go, negative charge will go together. But if I increase the electric field so much, what will happen? This positive charge will get blasted on the right hand side and negative charge will get blasted on the left hand side. Their attraction, force of attraction will be broken down, okay, due to so much electric field here. So that limit is called what? That is called dielectric breakdown, right? That maximum electric field that we studied previously. So if I apply electric field equals to the dielectric breakdown, what will happen? All these polar molecules or non-polar molecules, all these dipoles will get like separated, and huge number of charges, free charges will be present, and huge amount of current will flow that will simply damage this particular material. Okay, I hope we get the point. Initially insulator doesn't have any free charges, but after a certain threshold, huge amount of free charges we get huge amount of free charges, and due to that, basically all of this gets separated. And this K is what? This K is simply dielectric constant that I will explain in the next slide. Don't worry about that. Okay, don't worry if you couldn't understand. All these things is already we know. We have studied, we have solved questions. Just the theoretical part I am explaining it to you. Okay, there is another term. No need to. This is not that important. I will say here itself, not that important, but still you should know about this term. Not that important. Okay. So P vector, known as polarization vector, represents the dipole moment per unit volume. Just a term, that's it. Okay, how do I represent dipole moment per unit volume? So if you remember, your dipole moment was something like this, right? It was 2q into 2l vector, right? This was your dipole moment. L was from negative to positive, and divide by the volume. Volume is simply A times L. Okay, the like any volume you choose, any volume of the region you choose, A times L. So like the units of this actually is similar to sigma. Okay, sigma is what? Sigma induced. This sigma induced is what actually? This sigma induced is this. Whatever charge density there is on the outside, that is the sigma induced. I will show you how do we compute the sigma induced as well. I will show you that as well. Okay, so don't worry about that. So this is known as the surface charge density. So there is a relationship between the dipole moment and surface charge density. Okay, and dielectric constant we already know. This is what? This is just the relative permittivity that we have been using up until now. So just explain you the theoretical thing, not that important. This is what? This is E medium by epsilon naught, and it is simply epsilon r. This is the same thing as the relative permittivity that we already know. So no need to confuse. Dielectric constant is same as relative permittivity. Now can you solve this question? Okay, if you didn't knew all this theoretical concept, right, still you would have been able to solve this question. So pause the video and try to solve it yourself. An isolated 16 microfarad parallel plate air capacitor has a potential difference of 100 volts. So this case 1 and case, I will say this case A and case B. So in case A, my capacitance is 16 microfarad and my potential difference is 100 volts. This is 100 volts here. Now a dielectric slab with a relative permittivity constant of 5 is inserted in this region. Okay, so it has relative permittivity of 5 and same as the dielectric constant, filling the space completely between the plates. Calculate the resulting capacitance and potential difference in the new configuration. So will the potential difference be same or it will change? So here the potential difference between these two plates, right? Will it change? No, right? It cannot change. Okay, just I am applying some potential, it cannot change. Electric field will change now in this region. That is for true, that is for sure, but potential difference won't change. So basically case A is this, case B will be 1. So can you comment about the initial, let's assume that here I have electric field E0. So in case B what will happen? There is a dielectric here, right? There is a dielectric here. So if there is a dielectric, so K is 5. That is simply epsilon R. That's it. So what is my capacitance formula? Capacitance formula is epsilon A by D. A by D is constant, geometry is constant, just epsilon naught into epsilon R1, epsilon R A by D. So this particular thing is what, so initially my C, this is equals to epsilon naught A by D, correct? So this particular portion is only 16 micro. So I have to just multiply by 5. So this will be 5 times 16 microfarad. So this will be simply 80 microfarad. So only this thing has changed now. Okay. So my capacitance has changed now. What about the potential? What about the potential difference? So the potential, what is the electric field? Electric field inside the dielectric. The electric field inside the dielectric will become what? It will be E divided by E0 divided by K. So it will be E0 initial electric field divided by 5. Now one interesting fact you have to understand, yes, the potential difference between the two plates, is 100. That won't change. Okay, so that will remain same. Potential difference two plates will be 100 volts, but the potential difference in the dielectric, right? Potential difference in the dielectric will change. Why it will change? So potential difference in dielectric will change because the electric field has changed. Because what was my V inside a parallel capacitor? It was V was equals to V was equals to V E into D, and now E net has changed, right? E net is what? E net is simply E0 by 5 times D, and E0 into D was previously 100. E0 into D was previously 100, but now it has changed, so it will be 100 by 5, so it will be 20 volts. Okay, so potential will be 20 volts simply. Okay, so that is the, like, this thing you have to understand that, but they will not ask the question. This question will generally not get asked. Only they will ask the potential difference between the two plates. The potential difference between the two plates is still constant. It is 100 volts only, but just here the potential difference in the dielectric has changed. Okay, so that thing you should know. Another thing is, if multiple dielectrics are connected in series with each other, so what will remain constant here? What will be the same thing that will remain same? The electric field will be same, right? They are just multiple capacitors, different capacitors connected in series. So what was the C, like, what is this? Like here electric field is same, right? If you observe that my D1n will be equals to D2n and so on. This we have already derived. Just I want to derive an expression, special expression for this. So what is my C1 capacitance here? The capacitance here is simply epsilon R1, or I can say epsilon 1 A by T1. I will name thickness as T1. C2 will be epsilon 2. Area between the parallel plate capacitor are same only. it is T2, and so on. Okay, so overall what will it become? So my C, I know they are connected in series. So what is C equivalent? 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3 and so on. Okay, so what can I say? 1 by C equivalent will be what? This will be T1 divided by what? T1 divided by epsilon 1A. Okay, just I am replacing each capacitance, plus T2 divided by epsilon 2A plus T3 divided by epsilon. Okay, I will just write dot. Now what things can I take common? I can take common epsilon not common, right? I can take epsilon not common. So if I take epsilon not common, I can take 1 by epsilon naught A common. This will be T1 by K1 simply. K1 and epsilon R1 are both the same thing, right? Yeah, T1 by K1 plus T2 by K2, and it will actually I forgot to write one more thing, that until what it will go. So let's say this is the nth permittivity, and they have some space in between, right? They have some space in between. So what will be the space in between? The total space in between will be simply this D. I will write Cn here. Cn will be like the space due to the all the where the relative permittivity is simply 1. Okay, what is the distance for that? It will be simply, I will write here CO. It will be simply D, this total distance, not here actually, this will be epsilon naught A will be same. This will be total distance minus the sum of all the other thickness, correct? Sum of all the other thickness. So this will be 1 by C naught. So 1 by C naught here will be D minus sum of all the other thickness divided by epsilon naught A. So I can take this epsilon naught A common. So then this will simply become dot D minus T1 plus T2 and so on. Okay, so this C equivalent will, I can simply write this C equivalent in simpler terms. We can write just a simple formula I want to derive and nothing else, right? So this will be epsilon naught A, and this will go in the bottom. This will be simply D minus T1 plus T2 plus T3 and so on, plus T1 by K1 plus T2 by K2 and so on. Now basically let's understand how many types of insertion of dielectric slabs are there. So this is there are two types of dielectric slab. This is A and B. Now in each case can tell me what will be the equivalent capacitance. So if this is, let's say this capacitance is C1 and this capacitance is C2, what is happening? They are in simply series. Why? Because the normal component of the electric field is same everywhere. So I am talking about the normal component. Whenever I am talking about the normal component, capacitance will be in series, and this we already know actually. And whenever we are talking about the tangential component, the capacitors will be in parallel. Okay, C1 C2. So this is pretty simple, not that difficult to understand. Okay, so here the tangential components will be same, right? Tangential components will be same, that's why. So there can be two types of insertion of dielectric slab. One is series, another one is parallel. So either one works. So with the help of this concept, can you solve this question? This question is pretty simple. I will just show you the question. This is one question, this is another question, and this is the last question. So in GATE also they gave these type of questions. So this is the last question. Can you solve these questions for me? Pause the video and solve it for me. Now I will solve it in front of you. So this one is the first one. So this type of configuration we have already got. What am I observing? That this whole combination, the top one and the bottom one, are in parallel. Why? Because here tangential components are same, but this bottom, inside this bottom there are individual two capacitances which are individually in series. So things are pretty simple. So what will I write? I will first of all I will draw the equivalent circuit diagram to make my life more and more simpler. This I will name this as C1, this as C2, this as C3. Okay. So what is my C1? My C1 is simply now here I have talked anything about the relative permittivity. This is the relative permittivity, right? So C1 will be simply now the distance is same, but the area has been halved, A by 2. Area simply has been halved. So C1 will be epsilon naught into K is 4 into A by 2 divided by distance. This distance is same. This distance is simply this small d, right? So it will come out to be 2 epsilon naught A divided by D. C2 is what? Epsilon naught into K2, that is 3. Now here also area has been half, right? Area is halved, as well as what? As well as the distance also have been halved, right? This distance also has been halved between the plates. So this will come out to be d by 2 will get cancelled. 3 epsilon naught A by D, and C3 will be here also same thing, distance and area both of them are halved, so this will simply be 6 epsilon naught A by D. So what is your equivalent capacitance? Basically equivalent capacitance will be C1 plus C2 C3 by C2 plus C3. So what is happening over here? So this will be 2 epsilon naught A by D. So it will be at least more than 2 epsilon naught A by D. So just hold on. So obviously this option A is eliminated. It cannot be 2A by epsilon naught A by D, because simply it has to be more than this, because there is some positive term here. C2 C3. So C2 C3. So this will be what? 3 times 6 divided by 9. C, this is C square. Just I'm taking some common thing. Epsilon naught A by D, I'm taking it common. So this will come out to be what? You can take it to the next page. C equivalent will be what? 18. So this is 2C. C is epsilon A by D. So this will be 4 epsilon A by D. So what I did was, instead of writing epsilon A by D multiple times, I just chose it as a dummy variable. So what did I do? I just chose epsilon A by D as C, just to make my life simpler. So in examination as well, you can do something like that. So don't need to write epsilon A by D multiple times. Just write it as C and then cancel things out. So you will get option C as correct. Okay, it will be 4 epsilon naught A by D. So pretty simple, and in the next question also is pretty simple, but here just the difference is, here actually your dielectric constant is a variable. Basically it varies with respect to the distance. Okay, and this type of question we have done in in the lecture 1, I believe. Okay, so again this simple thing I hope you can do. So what will be the C? Like here you have to solve using basics. You have to solve using basics. So what is the what is the basic formula? So inside this small element, right, what is the capacitance? Basically if I choose a very small element, okay, then what will be the capacitance? Small capacitance DC will be equals to what? It will be epsilon into area is constant everywhere. Area is constant A, and distance is changing, right? Let's assume this has the X distance, okay, X direction. So this is epsilon A by X, and my epsilon itself is a function of X actually. What is it function of? Here they have mentioned, right? It is 1 by Y plus L. L is the, okay, K varies as Y. Okay, K is varying here. Okay, K is not varying in this direction. K is varying in Y direction. Okay, fine. I am varying in this Y direction. So if I am varying in Y direction, what does that mean? Now this question is very good. So listen to me very carefully here. So if I am varying in Y direction, right? If I just take a small strip here, over here, the length of this strip is dy. Okay, and I am moving in this Y direction. If I am moving along Y direction, what does it mean? If I would have moved along X direction, if this would have been individual slabs, what would have happened? They are all in series. But I am moving in Y direction. That means what? They are all in parallel. So I am not moving in X anymore. I am moving in Y direction. This distance is constant, that is L, right? No, L is the length of the plate, length of this plate. D is the separation between the plates. This is D and this is L. Okay, fine. So obviously if I am moving in Y direction, medium is varying along Y direction. This is a good question, right? If medium is varying along Y direction, what does it mean? It means that electric field, I am applying the boundary condition for tangential electric field. Here electric field and here electric field must be same. They are tangential, right? The interfacing medium is now tangential. So that means tangential. That means what? That means they are in parallel. If they are in parallel, then what I can do? I can simply add, like I will get some small capacitance delta C1, delta C2, so to infinitely small delta C infinity, right? So if I add C equivalent will be what? Summation of all this delta C, okay, from I equals to 1 to infinity, correct? But what am I varying actually? I'm varying y. So basically this integration, if I just want to make it continuous, what will I write? I'll write C equivalent will be integration of dc, okay, for y equals to 0 to y equals to L. Simply I'm adding each step, and I hope you know what is integration. So what is dc? Dc is this thing, right? Dc is simply this. So I will replace my epsilon y equals to 0 to y equals to L. I will replace my epsilon y. Epsilon y is given as this, right? Okay, epsilon naught into 1 plus y by L. Epsilon naught into 1 plus y by L. And obviously this thing is there, area divided by the distance. This thing is constant, right? Into dy. I am varying along y direction. So I will just remove the constant epsilon a by d. This will be outside. So what will be the integration of this? This integration will be y plus y square by 2l 0 to L. So this will be if I put L over here, this is L, this will be L by 2. So this will be 3L by 2 epsilon naught a yeah, area of the plate. This is square shape, right? If this is a square shape, I don't need to write here a actually. This a is what? Yeah, this is L square, right? This is L square actually. Okay, fine. But I am actually changing. This will not be L square. This will be L times dy. Why this will be L times dy? Because I am just taking a small element. So what is the area of this small element? The area dA of this small element is what? L times dy. Why L times dy? Because this distance is L, that is constant, and this distance is Ly. Okay, so what is the area of this particular thing, or this particular like small length? That is L times dl. Okay, so I should have actually written here, I've done a bit of mistake. This should have been actually dA. Okay, and dA is actually epsilon y into L times dy by d. Mistake on my here, sorry for that. So this will become, so a will not be here actually, just an L will be here. So 3 by 2 into L, so this will be L square by 2. And what is L square? As it is a square plate, they have written it is a square shaped plate, so L square is actually area of the plate, right? As it is a square plate, so this will be 3 by 2 epsilon naught a. Okay, so your answer will be 3 by 2 epsilon naught a, which is option C. So this is a good question. So I'll just quickly summarize what I did. First, I have seen that okay, I have relative permittivity, which is a function of some y. So I have to vary along that axis. So if I vary along y-axis, what you observe is my interfacing medium is in tangential to the relative field. That means they will be in parallel. So if I take each small capacitances, all of them I will add. Okay, for adding what I do simple integration. So what is the capacitance of a small element? What is the capacitance? It is epsilon naught a by d. Epsilon a by d, right? Epsilon is a function of y, so I will write it epsilon y. D is constant. D is not varying anywhere. So here the distance is always constant. But this y, right? What is this area? Area is what? What is the area of this small component? What is the area of this small component? Like the height of it is dy, and the other side is length L. That is not varying. That is same, right? This plate, that length L is not varying. So L times dl, not dl, sorry, dy will be my small area. Okay, small area, and that is exactly what I will replace here, and I will integrate basically my L from not my y from 0 to L, and like that I will get my equivalent capacitance as 3 by 2 epsilon naught a. So this is a good question, and this type of question can be asked in future gate examination. I am expecting these type of questions getting asked. Okay, so let's do another question. A parallel plate capacitor is partially filled with glass of dielectric constant 4 as shown. The dielectric strength of air is this and this. The maximum voltage which can be applied across the capacitor without any breakdown. So what am I observing? Are the capacitors in series or in parallel? What are they? They are in they are in series, right? Because the electric field and the interfacing medium is normal, basically they are in the same direction, right? So they are in series. So for series, what have I told you? Whenever dielectric breakdown terms come, just understand, are they in series or parallel? They are in series. That means you have to identify Q max. Q max will be minimum of Q1 max and Q2 max. Correct. So what is Q1 max basically? So I will take this as C1 and this as C2. Okay. So here what is happening is this parallel plate, right? The area is same for both of the dielectrics, just the distance between the plates has changed. Distance for this is 5 mm and distance for the other one is also 5 mm. Correct. So I will just find out Q1 max and Q2 max, right? What is Q1 max? Q1 max is E1 max. Like what is E1 max? E1 max is Q1 max divided by epsilon. If you remember, E1 max divided by not divide this time, A into epsilon. It does not depend on the perpendicular distance, right? It does not depend on the perpendicular distance. I hope you remember. Okay, it is constant. So here it is simply I will just write this in kilovolts only, 30 kilovolt into area into epsilon naught. That's it. Okay, what is Q2 max? Q2 max is E2 max into A into epsilon naught. Now you don't tell me at the last lecture of this how I got this formula. Don't tell me, okay? Don't tell me at the last lecture that how are I writing this formula. I didn't see this formula, so don't tell me that. Okay, so E2 max into A epsilon naught. So what is E2 max? E2 max they have given me as 300 kilovolt. So it will be 300 kilovolt into A. Now obviously there is, sorry, I forgot there is a dielectric here. So this will be epsilon R as well. Correct. This epsilon R is not 1 anymore. This is 4. So 300 epsilon naught into 4. So this will be 1200 A epsilon naught. Correct. So obviously which is much higher than this, but obviously I will choose the minimum of these two. So I will choose Q1 max. Q max will be 30 A epsilon naught. Now what I need to find out is what is the electric field basically here. What is the maximum electric field that I can like pass through this whole surface? That is 30 kilovolt, right? If I just divide this by A epsilon naught, what will I get? That will be the 30 kilovolt per centimeter. Correct. That will be the maximum electric field that I can pass through both of this. Yes. So it will be 30 kilovolt. Okay. Or what you can do is you can simply find out the potential as well. So what you have find out the Q max, right? This is the maximum charge that can pass through. Now I need to find out the potential. So what is Q max equals to? Q max equals to C equivalent into V max. Correct. So what is C equivalent basically? C equivalent is what? C equivalent is the equivalent of these two. How are these two connected? These two are actually connected in series. Now as they are connected in series, it will be C1 C2 divided by C1 plus C2. So what will be the series combination? Basically it will be epsilon naught A, okay, for C1, and divided by the distance is 5 only. So this I will choose for now, d by 2 into epsilon naught into epsilon R is also there for the glass, right? Into 4 into A divided by d by 2, and these two will be added simply. So epsilon naught A d by 2. So okay, what I will do is you can simplify this. So C dash or C naught is equal to epsilon naught A divided by d by 2. Correct. D is 5 mm. I hope you understand this point. D is 5 mm. So this will be C naught into epsilon R1 into C naught, because it is dielectric is 4. So 4 C naught divided by C naught plus 4 C naught. So this will come out to be 4 C naught by 5. So obviously what it will come out to be, so my C equivalent is what? This thing, right? This thing, which is Q max is almost 30 AE. 30 A epsilon naught equals to, remember that this is in kilovolt per centimeter, right? Remember this thing only, okay? This is the electric field. This will be equals to this 4 by 5 C naught, okay? 4 by 5 C naught. And what is C naught basically? C naught is equals to epsilon naught A by d by 2. Okay, so this epsilon naught A gets cancelled simply, they are in same units. So, and here what else is there? Obviously Vmax will be there. So Vmax will be equals to this, right? It will be 150 divided by 4, now divided by 8 into D. Now remember this is in centimeter, right? This is in centimeter. So I need answer is in kilovolt. I need answer in kilovolt. This is in kilovolt per centimeter. So I need to write this D in centimeter as well. So I will replace this D in centimeter. So it will be 150 by 8 into, this is what, 10 millimeter into 10 raised to the power minus 1, because 10 millimeter is 1 centimeter. This is in centimeters. Okay, so this will come out to be 18.75 kilovolts. Now there is a method 2 of doing this. Okay, easier way. Okay, what is the easier way? You have found out the Q1 max, right? What you can do, you can individually find out the maximum breakdown voltage of each of these combinations. So what will be the V1 max? Okay, this is the method 2. What will be the V1 max? V1 max is simply E1 max into D by 2. Okay, it is like for this type of question, it is good to do in this way. Okay, so E1 max into D by 2, because the distance, and E1 max is this. So what is E1 max? E1 max is 30 kilovolt per centimeter. So I have to write in again centimeter. This D is 10 millimeter divided by 2. So I will multiply 10 raised to the power minus 1 to convert this into centimeters, right? So we'll convert this into centimeters. So this one will come out to 15 kilovolt. Okay, and what is V2 max? The breakdown voltage maximum, it is E2 max into D by 2 again. E2 max is, if you remember, it was 300 kilovolts. 300 kilovolts into again 10 by 2 into 10 raised to the power minus 1 per centimeter. This is, so this will come out with 300 kilovolts. Not 300, sorry, 150 kilovolts. So obviously I can observe that I cannot apply 150 kilovolts because it will damage this particular device, right? So what I will do, because charge is same, as charge is same, then the potential also will be proportional to the charge, right? As I increase, what do I know? I know V1 is proportional to the charge because Q equal to CV. So as I increase my V1, Q1 will also increase. So I cannot increase my Q1 further than this. If I increase my Q1 further than this, it will get simply breakdown. So obviously I will choose the lower of the voltages. I will choose the lower voltages, correct? But it's better to choose with the charge case only. It's better, but you can choose it otherwise as well. How you can choose it? So you can use two things. What you can do is, now you know the V1 max, right? You know the V1 max. Now you compare with respect to the charges. So Q1 equals to Q2. If Q1 equals to Q2, I know C1 V1 equals to C2 V2. So once I will choose this as maximum, another time I will choose this as maximum, right? So if I choose V2 to be maximum, it is operating at its maximum rated capacity 150 kilovolts. What will I get? So what is C1? C1 is epsilon naught A divided by D by 2. C1 and C2 are almost same. Into V1, I don't know the V1, but I am operating the second capacitor in maximum rated condition. C2 is epsilon naught into epsilon R. Epsilon R is how much? 4. Epsilon R is 4. Into A is same, divided by D by 2. Into V2, I am operating in rated condition, right? 150 kilovolts. Okay. So this epsilon naught A gets cancelled, D by 2 gets cancelled. This will become, V1 will become 600 kilovolts, which will damage my device. Okay, damage my C1. So obviously I cannot use this. Again, I will go back, and that's why you need to do a cross check a bit. Again, you need to use the same formula, C1 V1 equals to C2 V2. Now I will use, first I use this as rated, and now I will use this as rated. Okay, 2 times I will do. So now if I do the same thing only, epsilon naught A divided by D by 2 into, I will use V1 as rated, so I will apply maximum 15 kilovolts on it. Okay, this will be equals to epsilon naught 4A divided by D by 2 into V2. I need to find it out. So what will be this equals to? This will be simply 15 by 4. Okay, so this V2 will be 15 by 4, kilovolts, which is well within my range, because V2 is less than V2 max, so it will not break down, and it is a safety net. But I cannot apply more potential, because some potential will be applied in V1 as well, and that will increase the maximum potential. So V max will be what of the combination will be as there in series. In series, what happens? The potential gets simply added. It is V1 and V2. So what will happen? V1 plus V2. So it will be 15 plus 15 by 4 kilovolts, which is 18.75 kilovolts, which is the same result that we got here as well. So two ways you can do, either this way or that way, whichever one is suitable. For this case, I think this one is more suitable. Okay, for a few other cases, that one may be suitable in terms of charges, whichever is given. If electric field is given, use potential. Okay, if electric field is given, use V. If charge is given, simply use charge. Okay, so yeah, that's it basically for this lecture, and with this we actually end our electrostatics chapter. This is a long topic, and yeah, it did required me more lectures, but trust me, what you have studied you for free, right? This is for free here, so you wouldn't have studied this in paid batches as well. In paid batches, I know how they teach you, like that is not much organized, and I myself has seen those things, right? Because I have also studied, and I have studied from different resources. So don't worry, whatever you learn the best thing. Just main thing is, whatever you learned, you need to revise and apply that in your examination. So you need to revise daily, and you need to apply those concepts in questions. You need to practice more questions. So but whatever I've covered, right, I've covered the complete syllabus, the maximum that is possible for a GATE student. So yeah, thank you for watching, and I will see you in the next lecture with magnetostatics. So that will be a new topic. We'll start with a new topic, and I hope you enjoy this whole series of electrostatics.